Stop whatever you're doing. Close your eyes for a second. Feel the chair beneath you, the floor beneath that, the building, the city. It all feels completely still, fixed, solid. Now here's what's actually happening. You are on a planet spinning at 1,670 kilometers per hour. That planet is orbiting a star at 107,000 kilometers per hour. That star, along with 400 billion others, is rotating around the center of the Milky Way at 828,000 kilometers per hour. And the Milky Way itself, along with every galaxy for hundreds of millions of light years in every direction, is being dragged through space at 2.2 million kilometers per hour toward something. Something so massive that it warps the motion of matter across a region of space so large that if you tried to cross it at the speed of light, it would take you 500 million years, and you still wouldn't be halfway done. And until 1986, we had no idea it existed. But here is the part that will genuinely unsettle you. The pull isn't coming from just one direction. While something colossal drags us forward, something else, a void of almost incomprehensible emptiness, is pushing us from behind. We are caught between two titanic forces, a cosmic tug-of-war. And the mathematics of that tug-of-war have only been worked out in the last decade. We are not falling, we are being launched. This is the story of the Great Attractor and the things around it we're only beginning to understand. Right now, without any sensation, without any warning, without anything in your daily life giving you the faintest indication, everything you have ever known is falling. Not toward the ground, not toward the sun, not even toward the center of the Milky Way. Everything our planet, our solar system, our entire galaxy, and hundreds of thousands of other galaxies surrounding ours is being pulled toward a single region of space at roughly 600 kilometers per second. Let's make that number real for a moment, because our brains weren't built for this. 600 kilometers per second means that in the time it takes you to read this sentence out loud, let's say 4 seconds, the Milky Way has moved 2,400 kilometers toward the Great Attractor, the distance from London to Cairo, in 4 seconds, continuously, without pause, for longer than the Earth has existed. The Milky Way has been doing this since before complex life appeared on our planet, before the oceans took their current shape, before the moon was close enough to cause the tides we know today. That's 2.2 million kilometers per hour, sustained, continuous, completely beyond our ability to stop or change. And the thing pulling us? We can barely see it. A significant portion of it is hidden behind the densest part of our own galaxy, blocked by so much gas and dust that optical telescopes see nothing but fog. We know something is there because of what it does to everything around it. The way a hidden stone shapes a current you can only read by watching the water move. We gave it a name. We called it the Great Attractor. That name sounds dramatic, and it earns every syllable. Here is the part that took decades to understand. The Milky Way is not special in this motion. We are not being singled out, pulled towards something while everything else stays still. Hundreds of thousands of galaxies are moving in the same direction, at speeds that increase the closer you get to the source. Galaxy clusters that contain thousands of individual galaxies are all converging on the same region of space. Whatever is doing this, it is doing it to an almost incomprehensibly large volume of the universe. To understand why this took so long to discover, you need to understand how astronomers first realized anything was moving at all. For most of the 20th century, the dominant picture of the universe was elegant and relatively simple. The universe is expanding. Edwin Hubble established that definitively in 1929, showing that galaxies are moving away from us in every direction, faster the farther away they are. This expansion is smooth, uniform, affecting everything equally. In that picture, galaxies don't have a peculiar motion of their own. They just ride the expanding fabric of space like raisins in a rising loaf of bread. each one moving away from every other simply because the bread is growing. But the moment astronomers started measuring galaxy velocities with enough precision to subtract out the expansion, something unexpected emerged. Some galaxies weren't moving exactly as the expansion predicted. There was a residual motion, a leftover velocity after you accounted for everything the expansion explained. Galaxies in a wide swath of the sky were moving slightly faster than they should have been in one particular direction. Not randomly scattered, coherent, organized, systematic, as if something in that direction had its thumb on the scale. Here is the first shock of this story, and it tends to get buried under everything that comes after. We didn't find the Great Attractor by looking at it. We found it by looking at everything else and noticing that everything else was leaning toward it. Think about what it takes to notice that kind of signal. You have hundreds of galaxies, each one moving for its own local reasons, being tugged by neighboring galaxies, by clusters, by local overdensities of matter. Each one has its own unique velocity, its own particular trajectory. And buried inside all of that noise, there is a coherent signal. Every single galaxy in a huge region of sky has a small additional velocity in the same direction that can't be explained by anything local. To find that signal, you have to measure hundreds of galaxies with extraordinary precision. Build a statistical model of what the expansion predicts. Subtract that model out, and then examine what's left. The people who did this were not a large collaboration with modern computing infrastructure. They were 7 astronomers working in the 1980s, before the internet, before modern supercomputers were routine tools in astronomical research. They did it by hand, or rather, by telescope time logged at observatories across multiple continents, painstaking measurements of galaxy distances using a technique called the Tully-Fisher relation, and years of analysis of the residuals. The group became known, informally, as the 7 Samurai. The name was a joke among colleagues, but it stuck. Their names were Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Donald Lyndon Bell, Roberto Terlevich, and Gary Wegner. They weren't looking for a great attractor. They were measuring galaxy velocities to understand how elliptical galaxies worked. The attractor found them. What they discovered was not a gentle drift. The velocities they measured were enormous. Not dozens of galaxies drifting slightly off course, but entire clusters of galaxies. Vast structures containing millions of individual stars, all streaming in the same direction at hundreds of kilometers per second. They traced the flow back toward its apparent source, and what they found was a region of space in the direction of the constellations Centaurus and Hydra, roughly 150 to 250 million light-years away. They couldn't see what was there clearly. They could only see the motion it caused. The paper they published in 1988 introduced the term Great Attractor to the scientific literature, and it immediately generated controversy, fascination, and a great deal of uncomfortable uncertainty, because what the numbers implied existed in that region should have been detectable, and it wasn't quite matching what observations could confirm at the time. The mass required to produce the velocities they were measuring was staggering. Not a single galaxy, not a cluster. Something on a scale the astronomy of the 1980s was still struggling to fully map. This is the first thing about the Great Attractor worth holding. We found it backward. We found the wake before we found the ship. The motion came before the object. Hundreds of thousands of galaxies announced something's presence through the direction they were falling before we could identify what they were falling toward. In the entire history of science, there are very few discoveries where the evidence of gravity arrived decades before the source of that gravity was understood. Now think about what that implies about the scale of what we're dealing with. To generate the kind of coherent flow the 7 Samurai were measuring, to pull hundreds of thousands of galaxies spread across hundreds of millions of light-years into a coordinated stream, you need an extraordinary concentration of mass. Regular galaxies don't do this. Even large galaxy clusters don't do this alone. What produces this kind of large-scale flow is a supercluster, a structure so vast that the word cluster barely contains it, a gravitational basin so deep that its influence stretches across a significant fraction of the observable universe. And there's one more piece to add here, one that makes the whole picture stranger and more vertiginous than even the Seven Samurai understood. We're not just being pulled, we're also being pushed. For decades after the Great Attractor's discovery, astronomers assumed the story was essentially a story about a pull. Something massive in one direction was dragging everything toward it. The motion of the Milky Way and its neighbors was the result of being attracted, gravitationally, to an enormous concentration of mass. That story is true, but it's incomplete. In 2017, a team of astronomers led by Yehuda Hoffman at the Hebrew University of Jerusalem published a paper that quietly rewrote part of the picture. They were using a technique called Wiener filtering to reconstruct the three-dimensional velocity field of galaxies in our region of the universe, essentially mapping the flow of galaxies and working backward to understand what distribution of matter could produce that pattern of flows. What they found on the opposite side of the sky from the Great Attractor was a structure they named the dipole repeller, an enormous void, a region of space with dramatically less matter than the cosmic average, that was producing a kind of anti-gravity effect on everything around it. Not anti-gravity in the science fiction sense, anti-gravity in a precise physical sense. When you are surrounded by matter on all sides except one, the gravitational pull from all directions partially cancels out, and what remains is a net force pointing away from the empty side. The dipole repeller is centered roughly 600 million light-years away from us, in the direction opposite to the Great Attractor. It is not pulling us. It is, in a gravitational sense, pushing us, because the mass that would otherwise balance the pull of the Great Attractor simply isn't there. Here is the shock. When Hoffman's team ran their models and tried to account for the total motion of the Milky Way, both in direction and in magnitude, they found that the dipole repeller accounts for roughly half of our total peculiar velocity. We are not being pulled toward the Great Attractor. We are being launched by a void and steered by an attractor. Two forces from opposite directions, working in concert, creating the 600 kilometers per second we've been measuring for decades. Think about what this means for the question of how the motion was interpreted all along. The Great Attractor was always a partial explanation. Astronomers had suspected the mass they could account for in the Norma cluster region was never quite enough to explain the full velocity. For years, the gap was filled by hypothetical mass hiding in the zone of avoidance, by the Shapley supercluster's contribution, by incomplete surveys. Some of that gap is real, but some of it turns out to have been the repeller all along, a force working not by attracting, but by its very absence. The universe, it turns out, is not just a landscape of mountains, gravitational peaks where matter concentrates and pulls. It's also a landscape of valleys, voids where matter is absent. And that absence itself shapes the flows of everything nearby. We live, cosmologically speaking, between a mountain and a valley. The mountain is pulling us toward it. The valley is pushing us away from it. Both effects are real. Both are significant. And we only understood this fully in the last decade. Let's go to the location. The Great Attractor sits roughly 150 to 250 million light-years from Earth, in a region of the sky centered on the constellation Centaurus. At its core, or at least what we've been able to identify as its densest region, is a massive cluster of galaxies called the Norma cluster, also cataloged as Abell 3627. This is a genuinely extraordinary structure. Thousands of galaxies packed into a relatively small volume of space, their combined gravity creating a deep well that surrounding matter falls toward. When X-ray telescopes finally began mapping it in detail, X-rays can penetrate the dust and gas that blocks visible light. The cluster revealed itself as one of the densest concentrations of galaxies near our region of the universe. But here is where the story takes a turn that the original discoverers didn't anticipate. and it's one of the most important pivots in modern cosmology. As measuring technology improved through the 1990s and into the 2000s, researchers began to notice something uncomfortable about the Great Attractor model. If the Norma cluster and the surrounding region were the whole story, the final destination of everything that was flowing, the numbers should have balanced. Map the mass, calculate the gravitational pull, check it against the observed velocities. Done. But the velocities didn't fully add up. The flow was too large, too coherent, too fast to be explained entirely by what was sitting at 150 to 250 million light-years. Something beyond the Great Attractor was pulling too. Look further past the Great Attractor, another 400 million light-years out. There, in a direction consistent with the overall flow, sits one of the largest known concentrations of mass in the observable universe, the Shapley supercluster. Named after astronomer Harlow Shapley, who identified the excess of galaxies in that region decades before anyone understood its full significance. The Shapley supercluster contains dozens of galaxy clusters, thousands of individual galaxies, and a total mass so large that estimating it precisely remains an active research problem. Its gravitational influence extends across hundreds of millions of light-years. The Milky Way is not just falling toward the Great Attractor. The Milky Way is falling toward the Great Attractor, which is itself being pulled toward the Shapley supercluster, in a layered cascade of gravitational influence that stretches across a significant slice of the observable universe. We are not in a two-body problem. We are caught in a gravitational drainage basin with multiple levels, each one deeper and larger than the one before it. Here is a number worth letting land. The Shapley supercluster is estimated to contain the mass equivalent of tens of millions of Milky Ways. Tens of millions. Our galaxy contains 400 billion stars. The Shapley supercluster contains in one concentrated region the gravitational equivalent of tens of millions of structures, each one containing hundreds of billions of stars. And even that number doesn't capture the full picture, because most of the mass in the Shapley supercluster, as with all large-scale structures, is not in the stars at all. Stop and consider what gravity actually means in the context of the Great Attractor. When we say the Great Attractor region is pulling us, we mean that there is an enormous concentration of mass in that direction, and mass produces gravity, and gravity produces the motion we measure. But here's the part that almost never makes it into popular accounts. The vast majority of that mass, roughly 85% of it, is not made of anything we've ever directly detected. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any way we know how to measure. We call it dark matter, and for the purposes of the Great Attractor's gravitational influence, it is not a minor contribution or an academic footnote. It is the dominant architect of the entire structure. The galaxy clusters in the Great Attractor region, the Norma cluster, the individual galaxies falling into it, the extended halo of matter around the cluster. All of this exists within a much larger, invisible scaffolding of dark matter that extends far beyond the visible structure. The X-ray maps that revealed the cluster's visible mass in such detail were mapping a kind of luminous tracer of a much more massive, invisible underlying structure. What we see when we image the Norma cluster is the small fraction of the total mass that happens to emit detectable radiation. The larger structure, the one actually doing most of the gravitational work, is invisible. This is not a fringe idea. It is the consensus of modern cosmology, supported by multiple independent lines of evidence: galaxy rotation curves, gravitational lensing, the large-scale structure of the universe, the behavior of the cosmic microwave background. Dark matter is real, in every observational sense that matters, even if its fundamental nature remains deeply, profoundly unknown. We have never detected a dark matter particle directly. We do not know if it is one type of particle or several. We do not know whether it has any interactions beyond gravity. We just know it's there, because the universe doesn't work without it. What this means for the Great Attractor is that when we say we're being pulled toward a concentration of mass, the mass we can see the thousands of glowing galaxies, the hot gas, the stars, is, gravitationally speaking, a minority player. The invisible scaffolding is doing most of the heavy lifting. We are being pulled, primarily, by something we cannot see, toward a structure that is mostly made of something we don't understand, at a speed we've only been able to measure accurately for a few decades. Take a moment to appreciate just how strange that is. The dominant force shaping the trajectory of our galaxy through the universe, the reason the Milky Way is moving at 600 kilometers per second in a defined direction, is fundamentally unknown in its nature. We can measure its effects with great precision. We can map its distribution. We cannot tell you what it is made of. And there's another invisible component making this even stranger: the cosmic microwave background, the CMB, the afterglow of the Big Bang, the oldest light in the universe, a bath of microwave radiation coming equally from every direction, is, in principle, the same temperature in all directions. The Big Bang happened everywhere simultaneously, and the radiation it produced should reach us uniformly. But when you measure the CMB with enough precision, you find a subtle asymmetry. One half of the sky is very slightly warmer than average. The opposite half is very slightly cooler. The difference is tiny, less than 0.001%, but it is there, and it is real, and it has a clear interpretation. We are moving. Our motion through space produces a Doppler effect in the CMB. The radiation coming from the direction we're heading toward is blue shifted to slightly higher temperatures, and the radiation coming from behind us is red shifted to slightly lower temperatures. The precise direction and magnitude of this temperature asymmetry tells us exactly how fast we're moving and in what direction, relative to the cosmic rest frame, the frame in which the CMB would be perfectly uniform. The answer it gives is consistent with everything else. We're moving at roughly 630 kilometers per second toward a point in the sky near the constellation Centaurus. The CMB is not just an echo of the Big Bang. It is, incidentally, a speedometer for our galaxy, and it's been telling us we're in motion for decades. We just had to learn to read it. What makes all of this even more conceptually interesting is the structure that maps the basin we actually live in. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a paper that quietly redrew the map of our cosmic address, using a new technique to trace the flow of galaxies, mapping the direction and speed of thousands of galaxies, and reconstructing the gravitational landscape those flows implied. They identified the supercluster we actually belong to. The structure they mapped contains roughly 100,000 galaxies, spread across an enormous volume of space. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is about 500 million light-years across. The Milky Way sits near its outer edge. The Great Attractor region, the Norma cluster and its surroundings, sits near its center of gravitational attraction, what the researchers called the attractor basin. Our galaxy, and everything in our region of the universe, is part of a single coherent structure with a defined gravitational watershed. All the galaxies within Laniakea are, in some sense, falling toward the same eventual meeting point. This reframing matters more than it might initially appear. Before Laniakea, the question of where we live in the universe had a certain answer. The Milky Way, in the local group, in the Virgo supercluster. That was our address. The Virgo supercluster centered on the Virgo cluster, a massive collection of galaxies about 65 million light-years away, was the structure we were considered part of. But Tully's team showed that the Virgo supercluster is not a self-contained structure at all. It's just one lobe of Laniakea, one tributary flowing toward the same gravitational basin as dozens of other structures we had previously considered separate. Our local supercluster was not an independent entity. It was a tendril of something much larger. Here is the part of the Laniakea story that should produce vertigo. We are near the edge of Laniakea. The Milky Way doesn't sit at the center of our supercluster. It sits in the outskirts, near the watershed boundary, the region where the gravitational pull of Laniakea roughly balances the pull of neighboring superclusters. We are almost peripheral, almost, but not quite at the gravitational boundary between two great cosmic basins. Understanding Laniakea requires understanding the broader architecture of the universe, because superclusters don't exist in isolation. The universe at the largest scales looks like a sponge, vast sheets and filaments of galaxies surrounding enormous empty voids. The filaments are where matter, concentrated under gravity over billions of years. The voids are where it didn't. Superclusters sit at the nodes where multiple filaments intersect, gravitational junctions where the cosmic web bunches into its densest knots. The Great Attractor sits at one of those nodes. The Shapley supercluster sits at another, larger one. Between them and around them are voids, regions where galaxy density drops to near zero, sometimes hundreds of millions of light-years across, that make the overall structure feel like a landscape of mountains and valleys, written at a scale no human mind can truly hold. There's something else at work in all of this, running against the grain of everything we've just described, and it's essential to the full picture. Dark energy. The force or the property of space, depending on how you frame it, that is driving the expansion of the universe, and doing so at an accelerating rate. While gravity is pulling the Milky Way toward the Great Attractor, which is being pulled toward Shapley, dark energy is simultaneously pushing everything apart at the largest scales. The expansion is winning at distances above a certain threshold, roughly a few hundred million light-years, and losing below it. What this means in practice is that the Milky Way will never actually reach the Great Attractor, not because it isn't being pulled, because by the time it would get there, hundreds of billions of years from now, a time frame that makes the current age of the universe look brief, the accelerating expansion will have pulled the Great Attractor itself out of reach. The destination is receding faster than we're approaching it. We are falling towards something we will never arrive at. That image deserves a moment. A river flowing toward a waterfall that keeps moving away. The river still flows. The current is still real. The direction is still defined, but the destination is permanently, irreversibly beyond arrival. We are passengers in a motion that has an origin, but no destination. Let's take the dark energy story to its logical conclusion, because the long-term picture is one of the most genuinely shocking things in modern cosmology, and it almost never gets the attention it deserves. Right now, the observable universe is roughly 93 billion light-years in diameter. The most distant things we can see are about 46 billion light-years away. That's a staggeringly large amount of space, containing hundreds of billions of galaxies, whose light has been traveling toward us for nearly 13.8 billion years. Every one of those galaxies is receding from us. The expansion is happening everywhere, at all scales. And it is accelerating. Dark energy, whatever it is making the expansion faster over time, not slower. Here is the consequence. The galaxies we can currently observe are, at cosmological timescales, drifting toward an event horizon, not a black hole horizon. A cosmological horizon, the distance beyond which the expansion is so fast that light from those objects can never reach us, no matter how long we wait. Galaxies that are currently visible to us will eventually cross this horizon and vanish from the observable universe permanently. The rate at which this is happening, and the time scale over which it will become obvious, is determined by the cosmological constant, the mathematical representation of dark energy, and the numbers are sobering. Within approximately 100 billion years, about 7 times the current age of the universe, all galaxies outside our local group will have crossed the horizon. The Virgo cluster, the Coma cluster, the Great Attractor itself, the Shapley supercluster, all of it will be, from our perspective, unreachable and invisible. Not because they've been destroyed, because space between us and them will be expanding faster than light can cross it. The civilization, whatever form intelligence takes 100 billion years from now, will look out at the sky and see only the galaxies of our local group. The Milky Way, Andromeda, the Magellanic Clouds, and a few dozen smaller satellite galaxies. The rest of the universe will be dark. Not just dark gone, in every practical sense. No observation, no signal, no information from beyond the local island of galaxies will ever reach them again. And here is the part that should produce genuine awe. They will not be able to prove the Big Bang happened. The cosmic microwave background, the afterglow of the Big Bang, the evidence we use today to understand the universe's earliest moments, will have redshifted so far into low-energy radio waves by that point that it will be indistinguishable from noise. The chemical signature of Big Bang nucleosynthesis, the specific ratios of hydrogen, helium, and lithium that can only be explained by the first minutes of cosmic history, will have been so thoroughly contaminated by billions of years of stellar processing that it will no longer be a clean signal. The large-scale structure of the universe, the cosmic web that we can trace today across billions of light years, will be invisible, because there will be no distant galaxies to trace it with. A physicist in that era, working only with the information available in the observable universe of their time, would look at the evidence and conclude correctly, given what they can see, that they live in a small island of galaxies floating alone in an infinite, static, empty void. They would have no way of knowing that billions of galaxies had already disappeared beyond the horizon. They would have no way of detecting the expansion, because all the things needed to measure it will have gone dark. The universe, at its largest scales, is not just expanding, it is erasing its own history, one galaxy at a time. We live at the one moment in cosmic time when the full picture is visible, when the universe is old enough to have developed structure, but young enough that the expansion hasn't yet pulled everything beyond the horizon. In a few tens of billions of years, the view gets permanently, irreversibly worse. We are, in some sense, the lucky generation. Not the generation that knows everything, but the generation that can still, in principle, see the whole stage before the curtain comes down. The Milky Way is not a convenient place to live, observationally speaking. From Earth, we look out at the cosmos through the disk of our own galaxy, a dense plain of stars, gas, and dust that bisects our entire sky. In the direction of the galactic center, the density is extraordinary. Billions of stars, layered one in front of the other. Clouds of molecular gas thick enough to block entire regions of the background universe. Dust lanes that swallow visible light before it can reach us. Optical telescopes looking in these directions don't see the distant universe. They see our own galaxy's interior, dense and opaque. This obscured strip of sky is called the zone of avoidance, not because astronomers choose to avoid it, because for most of the 20th century, they couldn't do much useful work there. Whatever sits behind the galactic plane, in the band of sky our own galaxy blocks, was effectively invisible to the tools available. And here's the deeply inconvenient part. The zone of avoidance covers roughly 20% of the sky. 1/5 of the universe's visible face, from our perspective, is behind our own walls. The Great Attractor sits partially behind the zone of avoidance. Its densest regions are in directions heavily obscured by the galactic plane. When the Seven Samurai were tracing the flow of galaxies back to its source in the 1980s, they were working with an incomplete map. A map with a large piece missing right in the middle of the territory they were trying to understand. Radio telescopes and X-ray observatories changed this, partially. Radio waves and X-rays penetrate the galactic plane much more effectively than visible light, allowing astronomers to detect galaxies through the fog that blocks optical observation. Surveys conducted with these instruments over the last 30 years have gradually filled in the map behind the zone of avoidance, revealing galaxy clusters that were invisible to earlier generations of astronomers. What they found there was not reassuring in the sense of simplifying the problem. It was clarifying in the sense of making the problem larger. In 2017, a team of astronomers analyzing radio survey data announced the discovery of an entirely new supercluster hiding behind the zone of avoidance. They named it the Vela supercluster. Located roughly 800 million light-years away, in a direction squarely behind the obscuring plane of the Milky Way, Vela contains what appears to be an extraordinary concentration of galaxy clusters. Initial analysis suggested its mass might be comparable to the Shapley supercluster, one of the largest known structures in the universe. And yet, it had been completely invisible to us until radio techniques improved enough to see through the obstruction. Think about that for a moment. A structure potentially comparable in mass to one of the dominant gravitational features in our region of the universe, hidden behind our own galaxy for the entire history of astronomy. We have been calculating the gravitational landscape we live in, tracing the flows of galaxies, trying to understand why the Milky Way is moving the way it is, and a potentially major contributor to that landscape was invisible to us until very recently. The map we've been working with has had a significant blank space right at one of its most important features. And if a structure as large as the Vela supercluster can hide completely behind our own galaxy for the entire history of modern astronomy, the obvious and uncomfortable question follows. What else is hiding back there? The zone of avoidance still hides a fifth of the sky. Whatever sits behind it is still being revealed, instrument by instrument, survey by survey, in the patient and ongoing work of mapping the universe we live in. The flows we observe almost certainly have components we haven't accounted for yet, contributors hiding in directions we can't yet see clearly, structures we'll name and measure in the decades ahead. Now step back and look at the full picture from the largest possible distance, because there's a dimension to all of this that tends to get lost in the details. The question of whether what we're finding is even consistent with our understanding of how the universe evolved. The largest confirmed structures in the universe are almost absurdly large. The Hercules Corona Borealis Great Wall, identified in 2013 and 2014 through the distribution of gamma-ray bursts, appears to be a filamentary structure roughly 10 billion light-years long, about a tenth of the diameter of the observable universe. The giant arc, identified in 2021, is a curved arrangement of galaxies and galaxy clusters about 3.3 billion light-years across. The giant arc alone is so large that if you were at one end and moved at the speed of light, it would take you 3.3 billion years just to reach the other end. A journey beginning before complex life appeared on Earth and ending somewhere in the far future. These structures are so large that they've generated genuine debate about whether they're consistent with our standard model of how the universe evolved. Whether a universe that should look smooth and uniform at the largest scales can actually contain features this big without that model needing revision. The cosmological principle, the foundational assumption that the universe looks the same in every direction at the largest scales, is, at this level, an assumption under active scrutiny. Not because we've disproved it, but because the structures we keep finding keep pushing the boundary of what largest scales means. Every time we've said, at scales larger than X, the universe is smooth, the next generation of surveys has found structure at scales approaching X. Here is the blunt version of this problem. Standard cosmological models predict that structures above a certain size, roughly 1 billion light-years, should not exist, because the universe hasn't had enough time for gravity to build them. Gravity is fast on human timescales, but slow on cosmological ones. It takes billions of years to build a galaxy cluster, tens of billions to build a supercluster. Structures that span multiple billions of light-years require either more time than the universe has been around, or some mechanism we haven't accounted for. Or, most unsettling of all, our models are missing something fundamental. We don't know which of those it is. That question is genuinely open, The data keeps producing structures. The models keep struggling to accommodate them. The resolution of this tension will likely require a next generation of surveys and, quite possibly, revisions to our understanding of how structure forms in the early universe. And there is one more anomalous structure worth naming, because it relates to everything we've discussed and pushes in a genuinely strange direction: the cold spot. In 2004, astronomers analyzing data from the WMAP satellite, a precision mission to map the cosmic microwave background, noticed an anomaly. One region of the CMB, covering a patch of sky roughly 10 times the diameter of the full moon, was distinctly colder than its surroundings. Colder, not by chance, but by a statistically improbable amount. The cold spot has been confirmed by subsequent measurements, including data from the Planck satellite. It is real. Explanations for it range from the mundane to the extraordinary. The most mundane: it is a statistical fluctuation, an accident of cosmic noise. The most prosaic physical explanation: there is a supervoid in that direction, an enormous region of space with less matter than average that stretched CMB photons as they passed through, cooling them slightly. A supervoid consistent with the cold spot's properties was indeed found in 2015. But there is an explanation, not the consensus view, not the favored view, but a possibility that physicists have taken seriously enough to publish peer-reviewed papers about, that is rather different. The cold spot is a bruise, a collision scar, the imprint of our universe colliding, in its earliest moments, with another universe. Bubble nucleation. The process by which inflationary cosmology predicts that separate universes can bubble off from an inflating parent space predicts that if two bubble universes collide, each one leaves a characteristic circular imprint on the CMB of the other. The cold spot's shape, size, and statistical properties are by some analyses consistent with such an imprint. Not proven, not consensus, but not ruled out. The cold spot remains, decades after its discovery, an anomaly without a universally accepted explanation, which means that the structure hiding behind our own galaxy, the supercluster we only discovered a few years ago, the flows of galaxies that turned out to have two causes instead of one, the dark matter we can measure but not see, the dark energy we can infer but not explain, all of this exists within a framework that may itself be a single bubble in a sea of others we will never be able to reach or observe. Now step back and look at the full picture. The Great Attractor is real. The flow of galaxies toward it is real. Laniakea is real. A coherent supercluster 500 million light-years across, containing the Milky Way near its outer edge, with the Great Attractor region as its gravitational center. The dipole repeller is real, pushing us from behind, while the attractor pulls us from ahead. The Shapley supercluster is real, pulling on Laniakea from further out. The Vela supercluster is real, adding another piece to the gravitational landscape that was hidden from us for the entire history of astronomy. All of this sits within the larger architecture of the cosmic web, a structure of filaments and voids written across the full observable universe, which sits within a framework that may extend infinitely beyond what we can see. But here's the question that doesn't get asked often enough, and it's the one worth sitting with. How far does the watershed go? The concept Tully's team used to define Laniakea, a gravitational basin, a region where all galaxies are flowing toward the same attractor, can be applied at larger and larger scales. Laniakea flows toward Shapley. Shapley sits within a larger web of structures. Those structures are part of even larger flows. At some scale, the flows become dominated by the expansion rather than by local gravity, and the concept of a coherent watershed dissolves into the general expansion. But between the scale of our galaxy and the scale where expansion dominates, there are layers of structure we have only begun to map. There's something genuinely strange about the scale here that's worth naming directly. A human lifetime is about 80 years. The universe is about 13.8 billion years old. In the 80 years of a single life, the Milky Way moves roughly 1.5 trillion kilometers toward the Great Attractor. That sounds enormous. It represents roughly 1/6000th of a single light year, a distance so small relative to the 150 million light years separating us from the Great Attractor that it is, for all practical purposes, nothing. The motion is real and continuous and measurable, and it will never, in any time frame meaningful to a human life, bring us noticeably closer to the source, which is perhaps the strangest way to describe our situation. We are in a river whose current is real and whose direction is clear, but whose destination is, for every practical purpose, unreachable. Not because the river stops, not because we change direction, because the universe is expanding faster than we can fall, and what we're falling toward is being carried away at the same time we're approaching it. The chase is built into the geometry of space itself, and yet we are doing something while we fall that no other known point in the universe has done, at least within our observation. We are watching, measuring, understanding, naming structures so large that the naming itself barely functions as a cognitive handle. We found the wake before the ship. We found the push from the void while trying to account for the pull from the attractor. We found Laniakea by mapping rivers of galaxies and following them to their source. We found Vela through an instrument that doesn't even detect visible light, probing through the walls of our own galaxy to map what hides behind them. Every discovery in this chain, the Seven Samurais paper, the identification of Shapley's influence, the Laniakea mapping, the dipole repeller, the Vela discovery, came from better instruments, more patient observation, and more sophisticated techniques applied to more data. The picture has been growing, step by step, decade by decade, not toward simplicity, but toward complexity. Each answer has raised more questions. Each structure found has implied larger structures beyond it. Consider what we know right now, in this moment of cosmological history. We live in a galaxy near the outer edge of a supercluster, 500 million light-years across. That supercluster has a gravitational center, the Great Attractor region, toward which we and all our neighbors are slowly falling, pushed from behind by an enormous void, and pulled ahead by a cascade of massive structures extending further than we've been able to fully trace. The boundaries of our observable universe extend 46 billion light-years in every direction. Within that sphere, there may be 2 trillion galaxies. Most of them are already beyond our reach. The expansion ensures that the number accessible to us will only decrease from here. We are in a river. The river is real. The direction is known. The destination will never arrive. And if that were all, if the picture stabilized here, it would already be one of the most astonishing things ever understood by any mind that has ever tried to understand anything. A civilization on a rocky planet orbiting an ordinary star, in the suburbs of an unremarkable galaxy, near the edge of a supercluster it had no idea existed until 11 years ago, has somehow mapped the large-scale gravitational landscape of the region of the universe it inhabits, has somehow measured flows of matter across hundreds of millions of light-years, has somehow detected the push of a void and the pull of structures hidden behind its own galaxy's walls. That is an extraordinary thing to have done. Extraordinary in the literal sense, so far outside of what could have been expected from the starting conditions, a small planet, some carbon, 4 billion years, that the fact of it is, if you take a moment to look at it directly, genuinely startling. The glimpse is still expanding. Every year, new surveys add data. New instruments reveal structure where fog was all we could see before. The James Webb Space Telescope is showing us the earliest galaxies forming in the universe's first hundreds of millions of years. The Vera Rubin Observatory, when it reaches its full operating capacity, will map billions of galaxies across the sky, producing a three-dimensional picture of large-scale structure with a resolution and completeness we've never achieved before. The flows we trace will become clearer. The structures will become better defined. The balance between attraction and repulsion, between dark matter's pull and dark energy's push, between the Great Attractor's influence and the dipole repeller's push, all of it will come into sharper focus. And whatever that sharpened picture looks like, the reasonable prediction, based on the pattern so far, is that it will be more complex than what we have now. Larger, more architecturally intricate, more deeply strange. The zone of avoidance still hides a fifth of the sky. The flows we observe almost certainly have components we haven't accounted for yet. The largest structures we've found so far may turn out to be the smaller features of an even grander architecture that future surveys will reveal. The cold spot may have an explanation that changes nothing, or one that changes everything. We don't know. That's not a limitation to be embarrassed about. That is the honest description of where we are, standing on a small planet in a river of galaxies, with instruments pointed in every direction we can manage, trying to read a map of something so large that the map making itself is a form of reaching for something we can never fully hold. Every second, 600 kilometers closer. Every second, the destination another 600 kilometers further away. Whatever the universe is doing with all of this, and it has been doing it for longer than we can meaningfully imagine, and will continue doing it long after every star currently burning has gone dark. It has, against all apparent odds, produced at least one place where something looks back. That something has been looking back for a very long time now, and the view, improbably, keeps getting better.